Okay, hi. Welcome to my humble abode and welcome to CSCI 6905, Compact Data Structures in Computational Genomics. So this is an introductory little video, and I guess I will sort of tell you what the course is about and how things are going to work, which this is the first time I've offered this course. I think this might be the first time anybody's offered a course quite like this. Um, the first part of the course will be about stuff that is covered in other courses, and therefore I'm going to use material from other courses, other people's courses in particular, Ben Langmead's courses in particular. Thank you, Ben. Um, so to give you an idea, I guess I'm just going to tell you now sort of what's the difference between computational genomics and computational pangenomics. Pangenomics is sort of the stuff we're going to try to cover, which is the term's been around for, I don't know, 10 years, maybe longer, maybe 15, 20 years. But it's really starting to heat up, and the tools are really becoming available now, and which is good because the shortcomings of what we were doing before are becoming more obvious. Okay, so, oh, I don't have my Illumina jacket on. Right. Okay, so the idea is, I'm going to focus on human genomics, but this also works for microbial genomics, plants, animals, various things like that. Okay. Stuff with DNA, which is basically anything living. Okay, so if you take, for example, a saliva sample or a blood sample and you send it away and you want your genome back. Now, this is not quite the same as if you just want your ancestry. If you send it to like 23andMe, where they just sort of, they check little parts of the genome, you actually want your whole genome. Now, this is important if, for example, you want medical diagnosis, you want to know what kind of variations you have, mutations you might have, or even inherited variations that can cause various diseases or conditions or whatever. Because if you send it away and people, for example, do microarrays or some technology like that, which doesn't give you a whole genome, then next week when they come out and they say, oh, this condition is linked to this variation on the genome, and you're like, ooh, well, they didn't test for that. So if you want to find out if you have that variation, then you have to go and get your DNA sequenced again, or checked, or whatever. Whereas if you have your whole genome, it's like, okay, well, you just go and look at that spot. So how does this work? So in the 90s, when they're doing the Human Genome Project, so okay, so you take your saliva, your blood sample, and you drop it into a machine, which is, these days it's usually, like most of the market is Illumina. And Illumina machines are short read technology, which means it takes a sample and it gives back little pieces of your genome. So your genome is about 3 billion characters for a human genome. And it gives back little pieces which are like 100, 200 base pairs. So the human genome, a character is a base pair. Right? So you have one thing that goes one way, and you have the double helix, and also you have like one that goes this way and one that's the reverse complement, blah, blah. You'll find all of this out in Ben's videos. So anyway, so it gives back 100 character substrings of your genome. And these overlap. So you have all these overlapping substrings, and the first time the Human Genome Project, okay, they weren't using Illumina machines, they were using a different technology, but if they had Illumina machines, they'd be like, oh, we have all of these substrings which cover the human genome. Back then it was like 10x, 20x. Now it's like, high coverage, like nice 50x, something crazy like that. So you have, say you have 30x. So instead of 3 billion characters, each character is covered on average about 30 times. So you've got about 90 billion characters. Right? So you have these little substrings, 100 characters, and you have enough of them that you have about 90 billion. Which is, okay, if there are 100 characters and you have 90 billion, you have about 1 billion of these reads. Okay, so these are called short reads. So the idea, if you've never seen a human genome before, like fitting these together would be like putting together, people say this is not something I've come up with, people say this would be like putting together a huge jigsaw puzzle when you haven't seen the box. Okay? But in the Human Genome Project, they fitted all these pieces together. So then you've seen a human genome. So they've actually produced sort of an aggregate reference genome. And so, okay, so now human beings are 19, I think I've read like 99.9, 99.8, whatever percent the same. So basically, like, you know, I have a heart, you have a heart. Everybody has a heart. If you don't have a heart, you're dead. Well, okay, you can have like an artificial heart, but you're still born with a heart. Right, so your DNA still codes for a heart. You know, you have a brain, you have skin, you have muscle, you have bone. If you're born completely without skin, you're probably not going to survive. I think that's probably very hard to survive without completely. Okay, so for example, if none of your muscles, so if you don't have muscle, if you don't have skin, if you don't have a heart, if you don't have a brain at all, you know, you're basically not going to probably live very long, at least not without a lot of intervention. So, I mean, the design for a human being is basically the same. The basic structures sort of the same. So there are little variations, but these are actually quite small. And so the DNA is basically the same. So this is great for if you're trying to put together a genome, because it's like, okay, well, we put together one jigsaw puzzle. So now we know what this box looks like. Now we're trying to put together, we have all these pieces. We took your blood sample or whatever and put it in the machine. Now we have all these pieces for this other jigsaw puzzle, for which we have never seen the box, but we've seen this very similar box. Okay? Good, good. So, so what you can do is, instead of trying to just take these pieces and fit them together and see how they go, you can like pick it up and like, yeah, okay, this piece, where does it look like it goes on this box? So this is approximate pattern matching. For each of these pieces, a lot of them are actually going to be exact matches to this box. Because Illumina sequencing, there are sequencing errors, but they're fairly few. I mean, I think it's about 0.1% now. Okay, so, and also, so you get maybe a couple of errors in each read, but not very many. So you're taking each read and saying, okay, what does it look like it goes on this box? And then you can sort of lay out the pieces according to this box. And so maybe there's a piece and it doesn't quite go, and you're like, yeah, but it looks a lot like this. So you put it there. And then afterwards, so you know sort of how these are laid out, and then you sort of, you can list the variations between this puzzle and the reference sequence. So this is good because it means you don't have to go to all of the work of the Human Genome Project again. And and also, now that you have this puzzle already, like as a reference, then you can sort of just take a big diff of this puzzle and this puzzle and store this one very compactly. So you don't have to spend 3 gigabytes to store a human genome, which, okay, so it would actually be, you only need about 2 bits per character, because they're only A, C, G, and T, adenosine, cytosine, thymine, guanine, and thymine, I think. So this is, I'm not actually trained as a biologist, you can tell. But I know people who were. Hi Rob, if you're watching this. So okay, you can store very compactly. So this is great. So okay, so this is, okay, these reads, you are aligning them to this puzzle. What's it called? It's called, the problem is called read alignment. And then if you list the variations between this new genome and this other genome, what's it called? It's called variation calling. And the format, you store variation or variant calling, I forget. Both start with V. So anyway, the format you store this in, if you store this as a diff relative to this other one, it's called variant calling format. or variation column, variant column format, I think. So okay, that's great. So how do we do that? So the Human Genome Project, there were like a couple of declarations of when it was finished, but I think it finished about 2000. So also in about 2000, actually exactly 2000. So there were two data structures invented. There was the compressed suffix array and based on the Boros-Wheeler transform, there was the FM index. I'm going to have to edit that. The FM index is invented by my supervisor. I can't believe I said that wrong. Hi, Giovanni. Okay, it's a bit late, but I should get this done tonight and post it. Okay, so there's the CSA and the FM index. And what these are, they're indexes. Okay. By the end of the first month, you should know and love suffix arrays and compressed suffix arrays and FM indexes. They're FM indexes based on the Boros-Wheeler transform, which while the CSA is based on the psi function. You'll find out about these things. I'm not sure Ben does this CSA, but I can tell you about it later. Okay, so these are data structures, and what do? Well, you take the reference genome and you index it. And that way, if you take a read and you hold it up and you ask, say, the FM index, and you say, this read, this little substring, where does it go? Where does it match in the reference genome? And this, the FM index, it takes the reference genome, and the really cool thing is, I mean, you could, for example, just index every substring of lengths between 100 and 200, right? Like in a big, big hash table, which is what people were using. There's, I think CARP and some people had a data structure called MAC. That's what people were doing. And they were big, and there were restrictions, and yeah. So, but the FM index actually takes the reference genome and compresses it. Okay, in the case of a single genome, it doesn't compress it very much, and in fact, the software, they were like, yeah, we don't care about the compression. They were like 2 bits per character is fine. We just don't want to use something like a suffix tree, which is like 90 bytes per character, something insane like that. So they were saying, okay, 3 gig. If it's 3 gig and the index is also about 3 gig, we're super happy. So this is actually about what it takes. So you index the reference genome, it's about 3 gigabytes. So if you hold up a read, and you say, okay, where does this read go? Now the thing is, the FM index actually does the exact pattern matching. So if you hold it up and the read happens to match exactly, then the FM index will tell you where it goes. So it will tell you, the super easy thing to do is it will tell you how many times it occurs, exactly. And then with some more tricks, you can find out all the places it occurs. By the end of this course, you will know why and how, and like all the ins and outs of, and can you get away with finding only one occurrence, and you'll know and love all this stuff, or at least you'll know it. So that's, spicy. So the FM index. So as I said, the FM index natively it does exact pattern matching. But then you can support, for example, inexact pattern matching by saying, okay, well, if I want to find all the places, so the read doesn't occur exactly anywhere. Well, what if it, maybe it's going to occur with one error, with one edit. Okay, so the edit, there's a substring in the reference sequence, the reference genome, which is at edit distance 1 from this read. How do I find that? Well, for example, what you can do is take the read and cut it in half. Now that means at least one of those halves has to occur exactly. So you can look through and find all the places you can search for each of these halves, and then for each of these places where you get a half, you see if you can extend it to something that's edit distance 1 from the other half. So this is what the part of the little half, or if you want edit distance, you want to allow edit distance 5, you cut it into 6 pieces. Okay, so by the pigeonhole principle, one of the pieces has to be there exactly. So okay, so this is the little piece. You cut it into these pieces, and the piece that you find exactly is called a seed, and then you try to extend it to an approximate. You try to extend the exact match of the seed to an approximate match of the whole reed. So it's called seed and extend. Okay. So there was a paper in 2004 by Lamb and some other people, including Wing Kai, I think. So Jamie may know more about this than I do, or at least he can ask somebody who knows more about this. So this was in 2004, and I think that the reason this didn't make as big a splash was like the computer science part, I think, was, so they were using the FM index, I think. Maybe, I think that was the FM index and not the CSA. But they were doing read alignment using an FM index, but aimed at a slightly different sequencing technology, I think. And then some more people came along in about 2009. So this was still sort of within the combinatorial pattern matching community, CPM. And it took a while, and then the bioinformatics people, the larger bioinformatics community found out about this. And in 2009, there were 2 papers which were by Langmead et al., hi Ben, and Lee and Durbin. And Langmead et al., there were 5, which were Langmead, Pop, no, I'm not sure, and Salzburg at the end, I think. I should know this, but it's late. If need be, I can find it out. Just Google it. So they did Bowtie 1, and then Bowtie 2 was just Langmead and Salzburg. And there's BWA. And they took sort of this idea of short read alignment with read alignment with FM indexes, but they did Illumina technology. I think this is, as a CS person also, I wasn't really paying attention at this point. So I think the difference was that it was aimed at Illumina sequencing. Okay. So great, fantastic. So everyone loves the FM index. So Bowtie 1 and Bowtie 2 together have been cited like 50,000 times, and BWA, something similar. And these are in use in research labs all over the world. But also, to some people, they would say, more importantly, also in clinics, hospitals. These are actually like, you have this sick kid, what's wrong with the kid? Well, you're going to sequence the genome, and how is that actually going to be done? It's going to be done using software, using Bowtie or BWA, which are basically FM indexes. So this is super cool, because this was, the M in FM was my supervisor. Like, wow. So you can see how I got hooked on this, and why I didn't go to Silicon Valley and figure out how to make people click ads and stuff and make a lot of money. Because this is like, oh wow, this is theoretically it's really nice, which you will find out when you learn how all of these things work. So I think the CSA was stock, and the FM index was Fox, or the other way around. So these are top level theory conferences. So this is really, Fox is foundations of computer science. It's really fundamental stuff, and people really appreciate this. But at the same time, it's saving people's lives, which is super cool. So, okay, so this is great. So everyone loves Bowtie and BWA. What's left? Okay. Well, around the time I was going to work with Giovanni, Gonzalo and Belli were looking at how to store. Okay, I'm doing this backwards. I'm telling you the CS stuff first. I should tell you the bio motivation first. So okay, we're almost all genetically, we're almost all almost exactly identical, almost exactly the same, almost, but not quite. And so sometimes those differences, they're small relative to the size of the genome, but right, so if I said 99.8, 0.2% is 0.2% of 3 billion is still a lot, right? So there's still quite a bit there. And in particular, if you 0.2% of your genome is messed up, it could kill you very easily. So the problem is, people found this use of one reference genome was creating reference bias. Because, so imagine that, so you have your reference sequence and you say, okay, well, this read, I'm going to look for it. You'll be like, well, it doesn't happen exactly. Okay, I cut it in half and I do a search. I'm like, well, I don't find either half exactly. Okay, well, I cut it in 6. Cut it in 6. So this means that I can tolerate an edit distance of 7. I was like, I still don't find it. Well, the thing is, it's possible that read, not only is it not, it's just not there. It's not like, oh, edit distance 8 or something. It's just that substring is really just not there. It's like you'd have to have a big edit distance basically, and you'd have enough edits to change it into something completely different to make it match. Because maybe it's a large, there's a piece of genetic material that's not in the reference sequence. So there's a paper by Sherman and maybe some other people, but at least one of the papers is just Sherman and Salzberg, same Salzberg. The same, this is like complexity theory. The same names keep coming up over and over again. So this is a problem. Right? So if you read some of the articles that are on the course webpage, in particular, there's one of them which it's from a site called Stat News, and it says, that there were these kids with a disease called Baratella-Scott, and the doctors know the mutation that causes Baratella-Scott, the variation, and they were taking the kids' tissue sample, saliva, blood samples, putting them in the machine, and the machine was saying, nope, they don't have that variation. So what was happening was it was taking the reads that actually had the variation in them, and it wasn't finding them in the reference sequence. So it couldn't sort of lay them out and sort of express it, because what was happening was it was taking the pieces and matching them to the reference sequence and saying, okay, this piece goes here, this read goes here, this read goes here, and then it had a little pile of stuff off to the side which didn't match. And that pile of stuff was what contained the variations that caused Baratella-Scott. Or more like read the article for the details. Or ideally, you can find something that's more scientific. Now, as it says in that article, it actually doesn't matter because there's no treatment for Baratella-Scott. So even if they could confirm that that's what it wasn't going to help anybody. Grim, but there are cases where this is a problem. You're getting somewhere you could treat. For example, in personalized medicine, you go in and they decide which drug to give you to treat your condition based on your genome. Well, if you have a variation, but it's not getting mapped, that could affect your treatment. And the problem is it means that people who look less like the reference sequence are going, personalized medicine is going to work worse for them. Now, this is discussed on the course webpage. There are several things you can try to do about this. For example, the reference sequence is not sort of the typical person. It was just somebody. Actually, it was an amalgam of several somebodies, about 70 somebodies, I think. But it's like one sequence. But it's not like they took the ancestral allele for every variation site. They were just like, yeah, maybe. So there, I think it's like the reference sequence, like the person is at an increased risk of diabetes or something like that. So there are several papers, or at least I think 2 papers linked to on the course website that talk about how to fix the reference gene, how to make it more standard. But the problem is you can only make it so standard. I mean, you can't make it close to everybody, especially given that you get these very different ethnic groups, and also they estimate that there's more genetic diversity within Africa than in the whole rest of the world, because when you had the out of Africa migrations, some people didn't leave, so only a few groups actually left. So, and then everyone else is descended from those groups. The groups that didn't leave, their genes are still in Africa, and not in anybody else. So there's a lot of variation in Africa that if you do studies based in the rest of the world, you're not going to find it. And so that is, we don't really have a good estimate of how much genetic diversity there is. And so finding sort of one typical human being is problematic, because who's to choose? So this should come up in, this should be discussed next week in the CGEM seminar on silent genomes. I'm not sure. I'm only going by the abstract, but it sounds like that kind of thing will come up, where they're talking about the problem of not having indigenous genomes in public databases. And so I'm going to see it because I want to watch it, because I want to listen to the seminar, because this is not my background either. I'm a data structures guy. So anyway, the issue. So one thing is like, okay, how do we have a representative reference sequence? So either try to make the single reference sequence more representative, or give up on having a single reference sequence. So what if you just want a few reference sequences? So originally, people were trying to say, okay, let's do a lot of reference sequences. But the problem is, FM indexes, sort of traditional FM indexes, break down if you just try to scale them up by a factor of 1,000. There are two components to FM indexes. There's the Burrows-Wheeler transform, which you will learn about, and there's the suffix array sample. And the Burrows-Wheeler transform, it actually, if you compute the Burrows-Wheeler transform of 1,000 genomes, and then you run length compress it, it's not that much bigger than for one genome. But the suffix array sample, if you take 1,000 genomes, either it's 1,000 times bigger or it's 1,000 times slower, or the factor by which it's bigger times the factor by which it's slower is 1,000. So basically, the product of the slowdown and the growth is linear in the increase in the size of the data set. So this is all from work by Veli and Gonzalo and Yoni and Nico. Going back to the earliest reference I found about this was a presentation, I'm not sure by Ioni, but it was a paper by Ioni and Gonzalo, not Ioni, Velni and Gonzalo, at a DIMAX workshop on 10 years of the Burroughs-Wheeler, 10 years of the Burroughs-Wheeler transform at DIMAX in 2004. So they tried to do that, and then they ran into this problem with the suffix ray sample. So that sort of got put aside, and then we resurrected it a few years ago. You will find that out when we get to the R index in the course. So you can't just scale this up. Yeah, you can do like 10 genomes. That's not a problem. You could build it now that we have bigger computers than we did 10 years ago. If you run Bowtie on 10 genomes, instead of being 3 gig, it'll be like 30 gig. Okay, because Bowtie really doesn't try to compress. It just gets it down to like 2 bits per character, and then it's happy. So 10 genomes are like, okay, well, what if you want, instead of, if you choose 10 representative genomes, like, yeah, okay, well, you still run into the same problems that 10 isn't really enough, especially if you don't just want to reflect ethnic diversity, you want to reflect, for example, rare diseases. So if you follow the links on, in the webpage, I think it turns out like rare diseases collectively are not that rare. It's something like 1 in 5, 1 in 7. I think it's that there are 7,000 of these things in people. There are 7,000 rare diseases that have been diagnosed in Canada, and something like 1 in 5 children has a rare disease, because even though each one is individually rare, if you've got 7,000 of them, then you've got a lot. So how do you pack like 7,000 rare diseases into 10 reference genomes? Like, while keeping them still typical. I don't know. But so that approach, so if you just randomly sample 10, you're not going to get all 7,000 rare diseases. If you engineer 10, this approach is called founder sequences. And we will study that. It's being investigated by Veli and other people in Helsinki. So I think Jarno will be showing up for the course. So I may have got hold of the wrong end of the stick. I may be underestimating what you can do with founder sequences. Jarno should know better. So keep an open mind until you hear it from Jarno. It's 33 minutes. Is there a time limit on this? So that's founder sequences. You have other approaches. You have De Bruijn graphs and PLAST. PLAST is like pangenomic BLAST. Essentially, what else do you have? You have the R index. You have hybrid indexing, PanDC, which is like running Bowtie or BWA over substrings sampled around the Lempel-Ziv 77 boundaries or relative Lempel-Ziv boundaries. There's a lot. I'm not going to try to pack it all into the introductory talk. So the R index, there's this new stuff we're doing, Money and Funny. Then there are variation graphs, which we're trying to actually do this thing. We're trying to resurrect the approach of indexing thousands of collections of thousands of genomes just as collections of strings. But a lot of people have gone, not a lot, but it's popular, have started doing this variation graph stuff, where basically you sort of think of an automata that accepts the language of genomes. And then you try to index the automaton. So it's like a graph where, think of it as a finite state machine. where so it's going to tend to be quite long, obviously, but quite skinny. Um, and the paths through this graph are real human genomes. So this is going to have sort of a buggy feature, which is it will accept even genomes that you haven't seen before, because when you take you take a collection of 1,000 genomes and you build this automaton, well, in order to it's a finite language, but when you put the states together and you take it from being a tree into being like a more compact automaton, it will start to accept stuff that it didn't accept before. So this is good because it means that if you see somebody who's not in that collection of 1,000, it will still accept the genome. It's bad in that you can get chimeric matches. We will discuss this and how people get around that using colors. Okay, so the software packages on that, there is, you will see some of this stuff at the end of Ben's indexing lectures when you get to Wheeler graphs, which was me, Giovanni, and Yoni a few years ago, but Yoni's been doing this for quite a while, starting with when he was a PhD student with Veli, and then continuing while he was a postdoc with Durbin, and now he's a postdoc with Patton in UC Santa Cruz, maybe? Anyway, so their software is called VG, and now they have this mapper tool for doing read alignment against variation graphs called Giraffe, which actually it was just posted on bioRxiv on December 6th, I think. So bleeding edge stuff. There's also this software called Minigraph by Heng Li. So when I said Yoni postdoc with Durbin, and now Minigraph is by Li, those were the Li and Durbin who did BWA. Like I said, it's just the same people. There are all these techniques. So this is sort of, I'm going to focus on human stuff because there's a lot of material and we don't have that much time, and we still want to talk about the data structures. Fortunately, the data structures are very similar for human or for microbial or whatever. I'm hoping that this course will appeal to people with backgrounds in computer science and in bioinformatics and in biomedicine, because this stuff really is important. So you can do fundamental computer science. For example, like I said, you can, FM index was, I think, Fox. Nicola has a soda paper. People have papers about building, so string synchronizing sets was Dominic Kempa and Tomasz Kosumaka, and that was in stock, I think. Sandeep Sinha had stock. Like there's a lot of nice theory. Nicola Contamaggio has a soda paper he will be presenting next week on sort of this automata stuff. And then you can go right from there to you can do sort of academic bioinformatics stuff, Recom, ASMB, stuff like that. And then you can actually go all the way over to like the places where constants really matter, where you're not just doing experiments, but so I remember about a year ago I was visiting. I was meeting with Christina at McMaster, and she was meeting with somebody from the hospital there, and he was saying that they really need these things to go faster. And he doesn't mean he wants them to go faster because he wants them to have optimal query time. He wants to shave off a log n factor, something like that. His motivation, he said, like, we need them to go faster because sepsis will kill a newborn in 4 hours. He's like, yeah, okay, so that's, you really need them to go faster. Now, I don't know, I can't remember if it was exactly 4 hours or maybe it was 6 because, or maybe it was 8, something like that. My brain is like, it's a constant, it's a small constant. I think in terms of big O. But some people actually want this stuff to go as fast as possible because, so Christina does antimicrobial resistance genes, and so does this guy. And the reason you need these things to go faster is because, okay, kid is sick, so you take like a sample, metagenomic sample. So you want to know what's in this kid has sepsis, so blood poisoning. So what's in this kid's blood, and in particular, what antimicrobial resistance genes does whatever the sepsis, whatever what's killing him, what antibiotics is it resistant to? Because if you treat them with the wrong antibiotics and the stuff is resistant, then it's not going to help. So you need to find out what it's not resistant to so that you can treat them with the right antibiotics and they will get better. And so what you want to do is actually sequence the genomes of the microbes in the kid's blood. So how do you do that? Well, you do it with an FM index. So this is super cool. So speeding this stuff up is actually, it's intellectually satisfying, but it's also, good for humanity. So that's my little motivational speech for the course. So the problem is, if you go, like I said, like one reference genome is 3 gigabytes. So now, I don't know if people know this textbook on data compression that was managing gigabytes. Like, okay, 20 years ago, gigabytes was a lot. Don't know when the book was published, but it's been around. Like, I think I knew it when I was starting grad school, so it was probably at least 20 years. I could look it up, but I haven't yet. I could email the author and ask where it was published, but then he would accuse me of being lazy. I know the author. Actually, know both the authors. Sort of. So gigabytes was a lot back then. Now it's like gigabytes, we don't care. So now the problem is terabytes. So you really, and the problem is, so if one sequence is 3 gigabytes. So if you want to do 1,000, that's 3 terabytes of raw data. Right? So now they have a data set. They completed the 100,000 Genomes project in the UK. So they have 100,000 genomes. So that's 300 terabytes. So, and an FM index, to be fast, it really has to be in RAM because it doesn't have good locality of access. Although we're going to talk about that using a technique that Yoni did in a paper this year or last year. Well, definitely last year, because it was not in the past week. If they don't have good locality of access, they really have to be in RAM to be fast. And that means you're dealing with, you want to be able to search quickly 100,000 genomes. If you don't compress them properly, it means that you're going to need 300 terabytes of RAM. There are computers with 300 terabytes of RAM, but not many, I think. I think if I absolutely needed to, I think Fabio said that at Max Planck there was a machine that we could get access to if we really needed it, and it had like 50 or 70 terabytes. I may be mixing up my prefixes saying gigabytes when I mean terabytes or vice versa. I'm a theorist, so it's like, yeah, it's really the same stuff. So it's not really the same stuff. It's just late. I need more tea. So there are all kinds of cool technical issues about taking these data structures, which work beautifully for 3 GB, and trying to make them to work for 3 TB or 300 TB. This is lots of fun. There are, what kind of queries do you want to support? How do you, okay, if you can't support the traditional queries, can you get the same functionality using other queries? And at the same time, this is cool because this is not just some intellectual exercise. There are people dying of sepsis out there, and they need these things. So okay, so the course is the first month. I don't know if everyone has the background about Boris-Wheeler, FM indexes, compressed suffix arrays. Some of you do. De Bruijn graphs, compact De Bruijn graphs, BOSS, all this kind of stuff. But to get everybody on the same page, I want you to watch Ben's videos. So the first month, there's this talk next week, the CGEM seminar. CGEM is Center for Genomics Enhanced Medicine. So this is one of the pluses about being at DAO. So there's the CGEB, which is Center for Genomics and Evolutionary Biology. CGEB, anyways, it's like bio. It's like more microbial stuff, I think. I just got here last year, and like this year has been weird, so I don't know my way around yet. And then there's CGEM, Center for Genomics and Enhanced Medicine, where they're actually trying to do things like personalized medicine, which is super cool. So when I can actually leave my apartment again, I hope I will actually meet these people in person, and we can actually work on something fun. So what do I want this course to be? So what I wrote in the syllabus was, okay, you learn about these tools, and then you do a comparison of two of these tools. That's sort of the baseline. That's if you don't have an idea of something else you want to do. What I would really like is, I mean, that's fine. That's fine. If you do that, that's great. Especially since a bunch of you I can't actually give credit to if you're not a DAO. If you're a DAO, fine. If you're not a DAO, I can write you a letter and say, yes, you took my course. And then if you need letters of reference to try to get postdocs or whatever, or faculty positions, then I can write and say, yes, you did this cool thing. So what I would really like is find something cool to do. So I listed some ideas. For example, this R-index thing where we modified the suffix array sample so that it doesn't get bigger, much bigger, and it doesn't, it only gets about as much bigger as the run length compressed Boris-Wheeler does, and it doesn't get slower. So we sidestepped that problem that Vali and Gonzalo were having, and Yoni and Nico, a couple of years ago, and we thought that was super cool. But then a few months ago, Takaaki Nishimoto and Yasuo Tabe figured out how to make it go even faster. And that's super cool. And as far as I know, it's not implemented. Maybe they're planning to implement it. It's online, it's on archive. Maybe they're planning to implement it. I emailed them and asked them. If they are planning to do that themselves, we shouldn't do it. But if they're not, then maybe somebody would like to do that and see if it actually, in practice, it really is faster. Now there's stuff out of Helsinki. Simon and Bella, they're doing another approach, which, okay, hands off. We shouldn't play with, like, if Takaaki and Yasuo want to do that themselves, good. Like, okay, we find another toy. But fortunately, Sharma said that he'd be super happy if somebody implemented a data structure called heaviest induced ancestors, which can, I think, could be used to find maximal exact matches, because it can find longest common substrings in LZ with respect to LZ77 compressed strings, and a longest common substring is the longest mem. So there's lots of cool stuff you could do, which isn't just a pairwise comparison. And the really cool thing is if you come up and you say, I have this idea, either I'm gonna do something, I'm gonna take one of these tools that exists and I'm gonna use it to solve that problem about faster sequencing for recognizing antimicrobial resistance genes in kids with sepsis. And be like, okay, I will try to put you in touch with the right people. I talk to Christine all the time, and you know, it's like, right, okay, you want to do that? Great. Especially if it works. If it doesn't work, you can still get an A. I remember, so when I was in Finland at Aalto, and I was having, and I just said, okay, look, I was teaching a data compression course, and I said, you can do whatever you want as a course project, but it has to be related to data compression. It has to make me say, wow. And everybody went off, and I didn't really tell them what to do. In fact, I didn't tell them what to do. They came back and they did amazing stuff. Some of it actually was published. One of them tried to do computing the Burroughs-Wheeler transform with GPUs. And he came to me with this project proposal, and I said, I think that's going to be really hard. Be prepared to fail. Like, not fail the course, but be prepared not to solve this problem, because I think a lot of people would like to do that. I think people are trying to do that. Actually, I think Paolo Faragina was trying to do that. I said, look, this is a really, really serious research problem. Go for it. He'd taken a course on GPUs. He'd taken my course on data compression string algorithms. He really wanted to do this. I said, go for it. But if it doesn't work, you have to write it up, and you have to tell me why it didn't work. You have to tell me what you tried and why you think it failed. And then you have to write it up nicely, which you're going to hate because you're going to be mad that it didn't work, but you still have to write it up. And so eventually when the course was ending, he came to me and he said, yeah, it didn't work. I'm super upset. I just tried and tried, but there's this bottleneck. I said, fine, I told you that you still have to write it up and you have to explain to me in the report what that problem was. And I like made him do this. And then I made him put his course report on arXiv. And then when people saw, like, I think a couple of years later, 2-3 years later, people solved it. And they cited his project report on arXiv. And that they wrote the conference version, they cited it, the journal version, they cited it. And you can read it, and it says, like, there are several issues to be dealt with in, building the Burroughs-Wheeler transform in parallel, as described by Eerola citation to his archiver, which is super cool. I was so excited about that. I emailed him about it and everything. He's in industry. I don't know if he cared. I think he might have answered. I think maybe he was happy. So if you don't manage to cure sepsis, I still want you to write it up, okay? Because it's science, it's research. As Einstein said, if we knew what we were doing, we wouldn't call it research. It can still be useful for people so they don't go down this, not make the same mistakes, but they don't go down the same, if they go down the same alleys you went down, they do that knowing what the obstacles are at the end. So maybe they will have an idea how to get past them, but they won't get, if they get stuck in the same way you do, then it's their fault for not reading your course report. Okay, I should finish up before that. So this course is very open-ended. I don't think anybody's taught. I mean, Pangenomics hasn't been around that long. I don't think anybody, like I said, Giraffe got posted on December 6th. So I'm pretty sure Giraffe has never been featured in a course before. I happen to know most of the people who built these indexes. I can beg, if we get stuck, I can beg them for tech support. I don't know that they will give it to us, but I'm on a first name basis with most of them, so we have a chance. I would like it. I really hope that I can get some people from CGEM and CJEB and some CS people, and that we get a nice mix so that the biomedical people know what we need to do, and the CS people know how to make the data structures do it. And there could be data structures designers and coders and whatever. I have high hopes. Don't know if these are gonna work out in real life, but as I said, if we knew what we were doing, we wouldn't call this research. This isn't actually supposed to be my research, the research component of my job. This is supposed to be the teaching component. But I'm going to try to go for, do I want to go for 4 more minutes and like finish at an hour exactly? Okay, this is a long introductory video. Is there anything else I need to say? Okay, we have a bunch of people from outside now. Logistics. We don't need to meet every week, especially since you have, well, we can meet every week. I was thinking that get 3 hours and then actually only use 1 hour. And that way you get like class time credit for watching Ben's videos, reading papers I tell you to read, watching Ben's invited talk at CEBIB, watching my invited talk at Milan, watching my CJEB talk, watching various other talks that I might be able to get hold of. And so maybe we can just meet on WebEx for a discussion for maybe an hour every week. I have these weird times, as it says on the course webpage, because that way maybe I can get people from other parts of the world to do a guest lecture recorded or like live, and then we record it on WebEx, and then they can actually be present, or they record it, and then they can be present for a discussion in the next sort of meeting hour. It'll depend who shows up, who's interested, who wants to do what. This isn't really a course where I can tell you what the material is, and I haven't done this before. And I want to leave it open-ended and very democratic. Anything else? So first class and next class. Well, not the next after the first, you know what I mean. Right, so there's this data structures in bioinformatics. You can register for it now. It's sort of February 11th and 12th, hosted by the bioinformatics. I know the acronym, but I've forgotten. The Bioinformatics and Algorithms Group at Milano Bicocca. Okay. So I'm going to end a minute before an hour because I can't, there's probably something I should be telling you, some logistical thing. Don't cheat. So this, oh yeah, maybe I won't get, don't cheat. Dalhousie is on the ancestral unceded territory of the people. We are all treaty people. This isn't the syllabus. There's some other stuff in the syllabus. No harassment, no discrimination, no, it's in the syllabus. Be good, be nice to each other. And I hope it all works out. My name is Travis. My email is travis.gagey@gmail.com. Email me if you have questions. Great. Okay, I'm going to finish 10 seconds early. Ciao.